Hello, my name is Asaf Levy, and today I'm going to talk about a smart new architecture for cloud scale storage. I'll start by reviewing the problems that cloud scale presents to existing storage architectures and how we can use the new technologies that have emerged in the last few years in order to develop a new scalable architecture that can deal with these issues. We used to deal with transactional workloads that had small IOs and dealt with small structured data sets, and archives which worked with large data sets and large IOs, but have low bandwidth in nature. Modern applications are different since they require large data sets and they typically deal with files and not records, but activity is very high. We need to serve a lot of IO at high speeds, and latency is also expected to be good. And another problem that these data sets represent is randomness. And randomness can be multiple things. It can be machine learning models that go over a very large data set and just read from all over the place. But there can be another use case in which a storage system is serving many applications and they all run at the same time. And again, this would look completely random to the storage system. When looking at the requirements of cloud scale storage systems, we see that things have got complicated. We need to deal with many petabytes of capacity and allow for the system to grow over time as the dataset grows. We need a system that is very resilient, since these kind of systems that are very large have big blast radiuses. We want the system to be able to fail in place and self-heal itself. And we expect performance to be consistent and not show latency spikes because workloads are random. In addition, we expect the system to be easy to manage and be affordable for these kind of huge data sets. And what we see is that legacy architectures just can't measure up. So over time, storage systems have evolved. We started with the scale-up system somewhere in the 90s, and this was a system that was good for file shares. It could deal with terabytes of data. It worked well with small files, and it provided a good solution for the workloads that used to exist in the 90s. Next, we had the shared nothing architecture. And this architecture allowed systems to scale to petabytes of data and were good stores for media content. It could deal well with large file and were based on sequential media. The next phase is the disaggregated shared everything architecture, which I'm gonna talk about in the next slides. And this is an architecture that is built for exabytes of data and for modern applications such as machine learning, deep learning, and analytics. So we'll start by reviewing the current architectures. there is an architecture based on shared storage scale out. And node can share media like scale up arrays. RAID can be efficient, typically 20 to 25% overhead, or three-way replication on a 4-node cluster that presents a 75% overhead. You need a big step function to scale, and it requires a shared SAS backplane, often proprietary. This kind of an architecture can also provide multiple storage domains. So the most common storage architecture today is the shared nothing architecture, and it's built from the basic unit of a scale-out node. A scale-out node would typically have a CPU, some amount of DRAM backed by a battery, and some amount of drives, which could be spinning disks, they could be SSD drives, or they can be a mix of both. And as I said, almost every scalable storage architecture today is based on this basic building block. And the first problem this architecture represents is that it's hard to pick the right size. Each node has its own characteristics. It has some amount of capacity and some amount of CPU power and some specific composition of drives. And this personality will define the performance a specific node can deliver. And as you scale the system, mixing different types of nodes is complicated. There are limitations around mixing these nodes, and if you don't do it right, then performance gets limited by the slowest piece. The second problem is data movement, because a shared nothing architecture by definition shares nothing. It means that when a node needs to process a request, it's often not the owner of the data that it needs to deal with, so it needs to ask some other node in the cluster to process the request for it. What this creates is constant data movement between the nodes in the cluster, which often reduces performance. In some cases, asking just a single node for handling the request isn't enough, and the classic case is a rename, which might move a file between two directories in a file system, and those two directories won't necessarily be owned by the same node. So in order to process a request, a node might find itself speaking with two other nodes in the cluster, and again, this creates complexity and slows things down. The ways that these kind of systems try to deal with the performance issues caused by the fact that the data has sole ownership is caching. And there are two types of caches. There is write caches and read caches. And the problem with the write cache is that it's dangerous, because data doesn't really get persisted when a write occurs. The data gets written to memory, the storage system acknowledges the request, and this transaction remains in RAM. Now, if something fails, then you need to trust the battery in order to make sure that data gets flashed to persistent media fast enough before all power goes down. And sadly, this doesn't always work, which makes batteries the #1 contributors to enterprise storage data loss. One more thing about these procedures is because they are rare, they often can have bugs simply because they don't get tested enough. Read caches presents a different problem because each of the nodes maintains a read cache of the other node state, and it does that because you don't really want to go to your peers for every request. Then it creates a cache coherency problem. If one node writes and updates the state of some file in the system, it needs to tell all the other nodes in the cluster about this change so they can update their cache. Now, it might be okay in a 4-node cluster, but when you look at the 100-node cluster, the chatter starts to limit performance. And eventually it creates a block to how much you can scale. And this means that these systems would often have a scale limit, some number of nodes that you just cannot pass. And often, even before you actually get to this limit, performance stops to scale linearly. You can get more capacity, but performance just doesn't go up as you would expect. The next problem is rebuilds. And when I mean rebuilds is the fact that when a node goes down, and a node might go down not because there is something wrong with its media. It might go down because there is a hardware failure with one of its power supplies, or the DRAM has an issue, or probably due to the more common issue is that software has bugs. And when a node goes down, it will take all of his media with it. And when this media goes down, it incurs a rebuild event. And these rebuild events can take very, very long time. And it happens because these nodes are often very dense. They can contain hundreds of terabytes of data. And now all of the other nodes in the cluster are busy with rebuilding these hundreds of terabytes that just got lost from the cluster due to a failure which isn't really related to the media. And what's worse with this issue is, setting aside the performance degradation, is that you are now at risk. The redundancy of data is lower until the rebuild event completes. So how do we solve all these problems? We start by looking at the fact that there are new technologies today that enable innovation. There is low-cost QLC flash that have become available in the last 2 years. There is NVMe over Fabric, which makes data access faster from remote, and there is persistent memory that allows storing transactions at a very, very high speed at a lower cost. And I'll go a little more into each of these components. So we now have lower cost flash, and this means that suddenly flash have become affordable. It brings the cost of SSDs down to levels that were never possible before, but it has two limitations. QLC flash write performance is lower than TLC and definitely the previous generations of MLC and SLC. And QLC drives also have lower endurance that systems that want to utilize these drives need to deal with. NVMe over Fabric encapsulates the NVMe semantics and makes a drive accessible from remote via Ethernet over RDMA or over InfiniBand. It lets a CPU access a remote drive with very, very low latency. And in practice, it breaks the control or ownership limits of SAS. It allows a system that contains a large number of servers to access a large number of disk drives, and these drives can be remote. And the last component I would like to talk about is 3D Crosspoint. And 3D Crosspoint is some kind of a hybrid between RAM and SSDs. It is somewhat slower than RAM, but on the other hand, it is persistent. You don't need supercaps or batteries anymore. It's bigger and cheaper than RAM, and as any disk drive that supports NVMe, it can be shared over Fabric to allow remote nodes to access it. So we have taken these three new technologies and started to think how we can design a new architecture that will solve all the problems that the current architectures have today. And we started by defining requirements and what we want to achieve as scale without limits on one hand, and without any compromises on consistency. We want resiliency not only to be linear, we want hyperlinear resiliency. We want bigger clusters to be more resilient than smaller clusters. We want everything to be global. And when I mean everything, I mean the file system namespace, I mean the storage pool, the data reduction, data protection, and basically every algorithm the system runs. We want to not force our customers to use proprietary clients. We want to have a system that can scale in different dimensions. And at the end of the day, we want the system to be affordable. In order to meet these requirements, we need to avoid bottlenecks. We need to make sure metadata structures are not monolithic, but instead are scalable. We need to make sure that there is no inter-node communication that limits the ability of the system to scale. We need to make sure there are no central managers or journals or excessive lockings. And all these things are just limits to scale, and I'll talk about how we avoid them during the next slides. So step one to our new architecture is disaggregation. And disaggregation means that compute and storage are no longer together in the same box. We can have a set of compute nodes that are on the top and has set of storage nodes at the bottom, but disaggregation alone is not enough. If we still maintain the concept of ownership, then some of those problems still reside. We still need to have inter-node communication in order for nodes to serve requests. The next step we can take is a shared nothing architecture. In this architecture, all of the nodes can see all of the storage media, but they still require caching and still require batteries because there is no fast media that allows them to respond quickly to requests. And we still have caching issues and cache coherency, so we didn't manage to solve all the problems. Eventually, the solution we got to is the disaggregated shared everything architecture. And it is composed of multiple principles. Compute and states are disaggregated. We have compute in front-end servers, and these compute nodes are responsible to process protocol requests, and they deal with storage services. The media is in highly available NVMe over Fabric JBOFs. And each one of the compute nodes in the cluster can access all the drives. Instead of batteries and caches, we use Optane. And this Optane allows us to store metadata and buffer writes in a way that is fast and does not require batteries or complex recovery methods. Data is stored in QLC drives. When we have this disaggregation between compute and storage, suddenly the compute nodes are not as important anymore. The compute node does not contain any state. They access the state that resides on the JBOFs. There is no DRAM cache anywhere. There is one shared copy that everybody can always access at the same time. So there is a single point of truth. If one of those servers fails, then we relocate a virtual IP to one of the other nodes in the cluster, and that's basically it. We don't need a rebuild, and the system keeps running. Servers run in containers, and we use containers because it simplifies deployments and it allows orchestration in a way that can make scaling of compute resources much easier. If there is a lot of load on the system, we can spin up more compute nodes. When loads go down, we can reduce the amount of compute nodes and move the CPUs to deal with other tasks. Now that we have the basic architecture, The next step is to build a file system on top of it. And a file system always starts with a main data structure. And this structure needs to support scalable growth. And while the system grows, performance is also expected to grow linearly. This means that the size of the system must not impact the metadata access time. And we achieve that by using linear data structures. Basically a hash table, because a hash table, no matter what its size, you can always access it in a single I/O operation. We also use consistent hashing in order to allow expanding the hash table without relocating all of the metadata when the system grows. So the main file system structure is based on a large hash table. Each file system element is rooted at this table, and multiple roots can be contained in each of these buckets, each of the hash table buckets. Each element in the file system, and an element can be a file, it can be a directory, it can be an S3 object or an S3 bucket, and it doesn't really matter because they're all basically the same thing. Each one of these objects or elements have a B-tree of its own, and parts of those B-trees can be embedded in the bucket, and this is important when we talk about small files. Metadata is stored on Optane, which allows very, very low latency when we need to perform metadata updates or access metadata. And when the system handles writes, then they land on the Optane drives within write buffers. And at a later stage, the data gets migrated to the QLC flash. So the file system structure and the architecture allows us to avoid the first problem, which is not doing any crosstalk on the I/O path. The system does, or compute nodes do not have data ownership, which create hotspots and require the consistent reshuffling of data. We no longer need to coordinate between multiple nodes in order to perform complex operations. All these problems just go away. When a server needs to handle a request, it can perform all the tasks on its own, and it doesn't need to ask for the help of other nodes in order to process the request. The main data flows of the file system have become very simple. In order to serve a write, a node simply receives a write request, writes the data to the Optane write buffer, updates the metadata to point to the new data that was written, and that's it. The write request is only processed by the node that got the request. The read flow is similar. You get a request, you look for metadata in the Optane drive in order to find out where the data resides. You read the data from either the Optane write buffer or the QLC in case data was already migrated. You decompress the data and you send it back. again, the only nodes that need to be involved in processing the request is the node that got the request. In the background, there is the data migration flow. And the data migration flow responsibility is to make sure the write buffer does not fill up. It reads data and metadata from Optane. It performs the more CPU heavy operations such as data reduction and rate encoding. And then it writes data in large stripes to the QLC drive. In contrast to the synchronous data operations, the work here is shared among all the nodes in the cluster. So it doesn't matter which node actually wrote the data. We have all the cluster helping out in processing the heavy load of reducing data and compressing it and encoding it. And this work is shared uniformly between all the nodes in the cluster. The next issue we want to avoid is central managers. And again, central managers can become bottlenecks. And again, the solution is simple. We just don't need them. All the data is accessible from everywhere. So if you want to read the state of a directory, or if you want to read a file, you just go to the media and get it from there. There is absolutely no need for a central manager. One thing that other systems often have are central lock managers, and we avoid that by using the RDMA compare and swap operation on the memory of the JBoss. The next enemy of scale are journals. And journals kill scale because once there is a failure event, the system needs to wait. And as the number of nodes in the system grows, so does the probability that one of the nodes in the system will fail. So we don't want journals. On the other hand, a file system and a consistent file system, as we wanted and stated that we need before, needs to support transactions. And we designed this method that support transactions without having a journal. So how does it work? Every file system operation gets a transaction ID or transaction allocated to it, and metadata block updates are conditional on the success of the transaction. There is a linear data structure in which transactions are committed to, and when a reader goes into a metadata block and encounters such a conditional update, it goes to the transaction registry and checks the state of the transaction in order to infer the state of the block. And since transaction state is resolved on demand, there is no need for a recovery operation when a node fails. And I'll continue with an example. And the classic example is rename, which is one of the more complex operations in file systems. So in our example, we want to move file X from directory A to directory B. And the classic implementation of doing that with a journal says, okay, we'll go to the journal and we'll say we're adding an entry. We want to move X from dir A to dir B. And then we're gonna lock dir A, lock dir B, make sure there are no deadlocks. And then we'll remove X from the metadata of directory A. We'll add it to metadata of directory B. Unlock, commit the transaction in the journal, and everybody's happy. With the vast transactions, it looks a little different. So we're gonna allocate a transaction ID, 1, 2, 3 in this example. And this transaction ID also contains something which is called the node instance ID, which I'll talk about later. We'll lock the directory A metadata block, and we'll add an entry inside the block which says that if the transaction is successful, we'll remove X from A. And then we'll unlock dir A. Next, we're gonna lock dir B, and we're gonna write a very similar thing. Then we're gonna write that if the transaction is successful, then we'll add X to B. We're gonna unlock directory B and commit the transaction. So it looks a bit similar, with one main difference here, that we don't need to keep both directories locked at the same time, which is an advantage to Scale because we have better concurrency. But the real difference is when we want to perform recovery. So once we have a failure and our consistency is based on journals, then now we need to suspend the file system access, because it is possible that the file system is in an inconsistent state. It is possible that now file X isn't in any of the directories, or maybe it's now written in both. So we'll go over the journal, and we found an entry called moving X from A to B. And now we need to check the consistency of the file system. So we'll lock dir A and lock dir B. We're gonna roll back their operation, unlock the directories. Now we can mark the entry as committed, and we resume file system access. So there is a relatively long point in time in which clients cannot perform IOs on the system. With the vast transactions, there is no need to suspend anything. The conditional entries remain in the directory metadata until at some point in time which a reader looks at this block and finds a conditional entry, and this conditional entry has a transaction ID, and when it wants to understand the status of the directory, it will go and check the status of the transaction. And if he sees that the transaction is not committed and that the node which is identified by the transaction ID is dead, then the entry can be discarded and recovery is complete in a lazy manner. The next thing we would like to avoid are locks, because locks are the enemies of Scale. They limit parallelism, which large clusters do. But unfortunately, we can't really avoid locks. At the end of the day, if we have two writers and they want to update the exact same block at the exact same time, locks are mandatory. But we have managed to narrow it down just to this case. There are no locks on the read flows, so readers are never blocked. It doesn't matter how big the cluster is or how many readers we have in parallel, they never block each other, and the system can scale performance linearly without any concerns. Another rule that we managed to keep is that we never need to lock more than one block at the same time. So lock contention is minimized to the time it takes to write a single block to an Optane drive, which typically takes somewhere between 10 to 20 microseconds. The reason is that this is possible is exactly because the transactional updates that we talked about in the previous slide. Metadata updates are conditional, so the file system is always consistent. There is no need to lock multiple blocks at the same time in order to make other reads. The next item, we would like to avoid our proprietary clients. And one of the main reasons other storage systems use dedicated clients is that they help the shared nothing system scale. And they help them scale because they can be made aware of data ownership. And they help these systems reduce inter-node communication. And they often work well, or work well, at least some failure happens and then the client needs to learn the state of the cluster. But they also have big downsides. Clients are hard to deploy and maintain. If you want to distribute a client, then you need to deal with compiling it to every known distro to man. And this is just a lot of work for an R&D organization. Clients often create delays in OS updates, which means that systems are left unprotected for a longer time and cannot benefit from frequent security patches that come along with the distribution's updates. And basically we just don't need it. There is no data ownership, so we don't need our own dedicated clients that is aware of how data is distributed in the system. Hyperlinear resiliency. So what does that even mean? What we want to achieve is a system that, in contrast to other systems which increase the probability of failures when the system gets bigger, we want to achieve the opposite. We want a system that the bigger it gets, the more resilient it becomes. And when looking at what a resilient system needs to deal with are usually two types of failures. There are hardware failures, and hardware is destined to fail. And there are software failures because software has bugs. The fact that the storage media is placed in a highly available JBOF and has no logic in it means that it's less likely to fail. First, because it's a simple hardware platform, and the second, because there are no software there, so the amount of software bugs that can lead to failures there is minuscule. Now, since every node in the cluster can access all the media, there is no need for more than a single node in order to maintain full data access. And as a product of that, when the cluster grows, the number of node failures it can sustain also grows. So even though a larger cluster can have more failures, the probability of failures of a single node increases. The fact that we don't need more than a single node to maintain access means that actually the cluster have become more resilient. It can sustain a larger number of failures. Taking a step back from the file system, we now see that we have achieved one of our earlier goals, which is a global storage system. And what it means is that since every node in the system can see all the media, there is no need to impose any limits. We don't need storage pools, we don't need to segregate the namespace, and we don't need small and inefficient RAID drives. And the algorithms we develop as a result of that are global. Data protection is global, endurance is managed globally, and data reduction is global. And more on that in the next slides. Data protection in our system is based on locally decodable erasure codes. The fact that all the media is available means that we can use very large stripes. And that means that stripes are somewhere between 36 plus 4 to 146 plus 4, depending on the size of the system. So we can sustain 4 simultaneous failures without any data loss. The locally decodable erasure code means that if a single drive is lost, then we don't need to read all the remaining drives in the stripe in order to rebuild the data, but we can do with only 1/4 of the drives. This is in contrast with the standard read Solomon that requires reading all the drives in the stripe. And work is distributed across all the servers in the system in order to allow for a faster rebuild. In very large systems, we can also make sure that the stripes are distributed in such a manner that we can even sustain an HA JBOF failure, meaning that even if an entire enclosure with all its SSD drives and Optane drives fails, the system can remain up. The next challenge that we need to address is QLC endurance. And QLC drives have the benefit of being much cheaper than their counterparts, but they also have the limitation of a lower endurance. And in order to keep the life expectancy of the QLC drives higher, it needs to minimize write amplification. And an SSD drive will have write amplification due to the fact that its internal NAND prevents it from writing new pages before an entire erase block is cleared. So data can be written in relatively small pages, but in order to rewrite a section and a large portion of the drive, typically hundreds of megabytes, need to be cleared before it can be used again. And this leads to internal write amplification in the SSD if a system doesn't take care of writing to it in a manner which is aligned to page sizes and is aligned to erase block. We also want to ensure there is no write amplification within the system. This means that we want to write to free space in the drives. We want to avoid in-place overwrites, and we want to make sure that data defragmentation within the system occurs as infrequently as possible. The way we do that is by utilizing our massive write buffer. And the write buffer resides in Optane, which is persistent. And since Optane is much cheaper than DRAM, we can have terabytes of write buffer space instead of gigabytes, which DRAM would allow it. This allows us to eliminate random writes and to coalesce writes. So how does it work? Writes are accumulated in the opt-in write buffer, and the life expectancy of each data block is determined according to various parameters such as the file extension, the folder the file resides on, and other parameters. Following that, stripes are written by their life expectancy, where ephemeral data is separated from longer-lived data. The shorter-lived data expires naturally once it gets deleted or overwritten by other pieces of data, which leaves very little data to garbage collect. The longer-lived data simply sits there, so there is no need to garbage collected, again resulting in a system that is not required to garbage collect a large amount of data and in practice reducing the system write amplification. The global nature of the system and the fact that we have a very large Optane drive allows us to store a very, very large exabyte scale compression dictionary. This dictionary allows us to introduce a new type of data reduction, which is called global data reduction and is based on similarity. As the data gets migrated from the Optane write buffer to the QLC flash, it is fingerprinted, and the fingerprints are kept in the global dictionary. If a similar block is found in the dictionary according to the fingerprint, then those two blocks can be compressed together, and only deltas are kept instead of full blocks. This creates a data reduction in a level that have never been possible before by more coarse algorithms such as deduplication. Once the architecture was completed and the system started to take shape, more benefits start to arise from this architecture. The first is the asymmetric nature of the architecture. Since storage and compute are disaggregated, we can scale them separately. So when the need arises, we can add more CPUs separately, or we can add more storage separately. What we also achieve is future-proofing, since today's hardware is slower and more expensive than tomorrow's hardware. And tomorrow's hardware is more expensive and slower than the hardware we'll have in 2 years. So a system that is composable and can scale independently each of its components allows us to evolve the system in a way which was not possible before. Another advantage of the architecture is that it allows for CPU pooling. If we have two workloads that we want to separate, or if we want to give quality of service to specific workloads, we can separate the compute nodes into different pools and have each workload work on a separate pool. This way we can, for example, separate batch workloads from interactive users and give each type of application the latency and the service it requires without interrupting the other application. CPU pooling is also flexible, so when the need arises, we can move nodes around between each one of those pools in order to match the required service to the current needs of the applications. The next advantage is what we call the virtuous circle of consolidation. Once you use low-cost flash for archival data, then suddenly you can use low-cost flash for all your data. The reason is that endurance is amortized because erase cycles that are not used by archive can be applied to transactional I/O. Performance is then maximized because the more flash we have, the better the performance gets. So we get a system that can suddenly serve all types of I/Os, all types of applications. It is fast enough because it is based on flash and a lot of it. And it is cheap enough because we are using low cost, low endurance flash. Also, the fact that the data sets are very large allows the global data reduction to work better, since there are more opportunities to find similarity within the data set. It all comes together in a product we call the Vast Data Universal Storage, which is based on the disaggregated shared everything architecture that I have described in the previous slides. It supports various protocols, and it is based on containers that run on physical servers and are connected with an NVMe over Fabric, commodity Ethernet or InfiniBand to a set of NVMe enclosures and offer a global namespace. We currently support two types of servers. The first is a quad server offline, which is used for compute. And the second is a highly available NVMe over Fabric enclosure, which contains 18 terabytes of Optane and 675 terabytes of QLC flash. One use case that demonstrates the ability of the system is a test done with an DGX A100 server that shows how we can get to 160 gigabytes a second with a single NFS mount on top of a vast system that contains 5 enclosures and 5 servers. So thank you very much for getting to this point in the presentation, and questions are welcome.